Since we have passed the part where we were talking about the Ethereum design and moved on to its applications, I have collected some notes, and I hope that it will help summarize the things we have seen so far about Ethereum. So Ethereum deals with accounts, and an account can be either externally owned, so either externally owned account, which is kind of equivalent to a wallet account in Bitcoin. So in Bitcoin, everything is a wallet account. But Ethereum also has a contract account. So this is an account that has code, has a smart contract. So each account has an address, and the address of an externally owned account is determined by the public key. So you would use a wallet to create a public key and a private key, and then the address will be derived from the public key. For a contract account, I believe this is actually done by hashing the content of the contract code with the nonce of the sender, of the creator. So each account anyways has an address. We established that. It has a nonce. So nonce stands for, I think, number ones. So it's a number that is only used once. It doesn't have to be consecutive, but I think in Ethereum it should be consecutive. The most important thing is that you never use the same number twice. The account has a balance in Ether. And if it's a contract account, you will also have code. So that is optional, and that's only for contract account. And if it's a contract account, it will have some storage associated. Now, the state of Ethereum is the state of all of these accounts. So for each account, knowing the address and all this, and this represents the current state of Ethereum. The only way for that state to change is to apply a transaction. So transactions can either be sent from the outside by a user, by submitting a transaction to the network, or by a smart contract itself. So the goal of a transaction is to change the state of the Ethereum state. No, it's the state of Ethereum. The input of a transaction, the parameters of the transactions, you have the sender, so whoever initiated the transaction, that's either the smart contract or the externally owned account, in which case you will have to add a signature. And it has a destination, so if either you send to a smart contract or you're sending to another wallet. It also has a number of Ether that you are transmitting, and optionally you can have some data. So arbitrary amount of data, some arbitrary binary data that you add to the transaction. And finally, if we are talking about contract, you are calling a contract, it will also have these two numbers, the start gas and the gas price. So if the destination is a smart contract, you are going to execute a function on that smart contract. And each instruction that is being executed will cost some gas, and that depends on the particular instruction. Some instructions will cost more than others, of course. If as you are running the function, you are running out of gas, then the state will not change. So everything will be reverted to the current state. So no change will be applied. But you will still pay the fee, and the fee is the product of the start gas by the gas price. So a smart contract, what does it have? It has some code. So it's similar to a class, which basically has a bunch of functions and a bunch of storage. When you call a smart contract, you would get input data from the transaction, that data part from the transaction, and as it runs, it would have access to temporary storage in the form of a stack, memory. So stack is, as its name implies, it's values that are organized as a stack, last in, first out. Memory is organized as an array, of a direct access array. And finally, storage is where you would put data that you want kept between execution of the smart contract. The other two, the stack and the memory, will be wiped at the end of the contract execution. The smart contract can call other smart contracts, so you can nest function calls basically, and in that case, the smart contract will also have to pass a gas limit. But the difference is that if the inner call fails, the state is not reverted to the original state, but to the state before the call was made. And then you have the smart contract has the ability to create other smart contracts. So the idea here is that a smart contract can do pretty much the same thing that a transaction, external transaction, can do, contrary to Bitcoin. All these transactions will be stored eventually in the blockchain. So there will be transactions floating around before they are included in the blockchain for verification, but in order for them to be considered permanent, they will have to be included in the blockchain. So it's very similar to Bitcoin. The blockchain payload will be a list of transactions. Beyond that, besides that, the blockchain is obviously a collection of blocks. So each block has this this list of transactions that are ordered. Each transaction has to be executed one after the other. And in the header, it has also the hash of the previous block, so that it forms a linked list. It also has the block number, the current difficulty for the proof of work, and the new thing here is that it also has the state root hash. So that's the root hash of the Merkle tree that is built from the state, the Ethereum state. So again, the Ethereum state is this information for each account. This is a quick summary of what we have seen so far in the white paper. I think the only thing I forgot was to say that the smart contract language is a complete Turing machine. So it has loops and storage, contrary to the scripting language of Bitcoin, which does not have either loops or external storage.